10.9 Taylor and Maclaurin series. In the next two lessons, we will investigate operations on Taylor and Maclaurin series and study some techniques and shortcuts for finding a power series that represents a given function. Let's develop a procedure in general for writing the power series for a given function that will have derivatives of all orders. We will find that every convergent power series must take on the form, and this is the form that they're talking about. So, form of a convergent power series. If f is represented by a power series, f of x equals the summation of a sub n times x minus c to the n for all x in an open interval containing c, then a sub n equals the nth derivative of f at c divided by n factorial. And f of x equals f of c plus f prime of c times x minus c plus f double prime, sorry, there's a mistake there, that should be double prime, f double prime of c divided by 2 factorial times x minus c squared plus dot dot dot, and then this is the nth derivative at c over n factorial times x minus c to the n. Note, be sure you understand that this theorem says if a power series converges to f of x, the series must be a Taylor series. It does not say that every series formed with the Taylor coefficients, a sub n equals f, the nth derivative of f at c divided by n factorial will converge to f of x. The formal definition of Taylor series is stated below. So what they're saying is, when they're saying that if it converges to f of x, that means that, you've got your normal series, like let's say we've got, sine, and we all know what the sine function looks like. And let's say we wanted a first degree Taylor polynomial for sine. Well, it's just going to be y equals x. And then what about a second degree? Well, a second degree is like just that. It's like a downward facing parabola. I think it's like minus x cubed. Actually, it might be a cubic function, because I think it's minus x cubed like that. I think that's a second term, so it goes up like this. But what I'm trying to say is that each time, so let's say that this was, the second one. So each time you can see that, the amount where it is actually equal to the sine function is getting bigger. Like on the first one, when it was just y equals x, it was probably only the same for that one point, x equals 0. But then when they used x minus x cubed, and it might have been, now that I'm thinking about it, over 3 factorial or something, that it's going to be convergent for a wider interval, okay? That means it's going to be exactly the same thing as f of x for a wider interval. So, you can have convergence to the function at a point or at a small interval, or it can be convergent. Like if you keep going to infinity with this Taylor polynomial for the sine, it turns into the sine function. It completely just is the sine function the whole way. So, but you have to go to infinity. Like whenever you stop, that's when it stops. Let's say we stopped right there. Well, the sine function would keep going on, but your interval of convergence would stop. Because if that was, let's see, what if we stopped there? Then it would be exactly the same for a larger number of x values. So here is our definition of our Taylor and Maclaurin series. So we have if a function f has derivatives of all order at x equals c, then the series summation n equals 0 to infinity, the nth derivative at c divided by n factorial times x minus c to the n is equivalent to f of c plus f prime of c times x minus c plus dot dot dot, the nth derivative at c divided by n factorial times x minus c to the n plus dot dot dot. This is called the Taylor series for f of x at x equals c. also, if c equals 0, it is the Maclaurin series. So the Maclaurin series is when you're centering it at 0. So our Taylor series shortcuts. We are going to talk about some shortcuts. I want to remind you what e to the x is. The Maclaurin series for e to the x. If you went and you did all the derivatives for e to the x and all of the f of zeros and f prime of zeros, you would get 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... plus, and then, well, actually, I'm going to stop it there, just plus ... And then I'm going to say that that is equivalent to the summation from n equals 0 to infinity, x to the n divided by n factorial. Okay, that is your general term. Okay, that's your summation, and that is what it's equivalent to. And if you then said, oh, well, I'm going to use that to find my Maclaurin series for e to the negative 2x. So e to the negative 2x, well, you're going to be putting negative 2x wherever there is an x in the e to the x Taylor polynomial. So 1 plus, and then I would say negative 2x plus negative 2x squared over 2 factorial plus negative 2x cubed over 3 factorial plus negative 2x to the 4th over 4 factorial plus ... And this one is going to equal, now let's just see what happens here when we simplify. This is going to be minus 2x. This one is going to be plus 4x squared over 2 factorial, which you could reduce, but we're just going to, show the factorial this time. This is going to be minus, next one's going to be minus, 8x to the 3rd over 3 factorial, plus, and this would be 16x to the 4th over 4 factorial, plus ... And so our summation for this, from n equals 0 to infinity, I know that it is going positive, negative. So I do want a negative 1 to the n or a negative 1 to the n plus 1 or something. I also want to make sure that whatever I make, notice that this 2 is 2 to the 1st, this 4 is 2 to the 2nd, this 8 is 2 to the 3rd. So I actually got my 2 to the n, because if I go to 0, that's going to be, if I start at 0, that's going to be negative 1 to the 0 power times 2 to the 0 power. That's going to be 1. So, I want to make sure that I get 1 as my starting point. And so I also have to make sure that my x's are there. Well, I can also take my x to the n, because look, this would be x to the 0 here, x to the 1st, x to the 2nd, x to the 3rd. And then you are dividing still by n factorial, because really this is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial that you're dividing by. So there's your general term for e to the negative 2x. And you could, put that together if you wanted to. And they only wanted the first 4 terms, 1, 2, 3, 4, so I really only needed this many. Those are your first 4 terms. And the general term, so this basically is your general term. So your summation, it didn't say you had to have your summation, but if you wanted to, you could make this negative 2x to the n over n factorial. They're all to the n here, right? And so go ahead and put all of them in and see if it works. 0, that would be 1 over 0 factorial, which would be 1. And if it's 1, it'd be negative 2x over 1 factorial, which is negative 2x. If it's 2, it would be positive 4x squared over 2 factorial. So, you know, this is going to work whether you leave it like this or whether you make it the negative 2x to the n. And then for part B, use your answer to find a Maclaurin series for f prime of x. Well, here's where you can, if they want a Maclaurin series for f prime of x, usually we call the Maclaurin series like a polynomial, like p of x, so p prime of x. Well, I don't know if they're going to like it written like that. Let's just say that f prime of x is equal to, and now you're going to take the derivative of every one of these. So the derivative of 1 is 0. The derivative of negative 2x is negative 2. The derivative of 4x squared over 2 factorial, you're going to bring the 2 down. It's going to cancel with the 2 in the 2 factorial. And so this is going to be positive 4x to the 1. And then you'll bring your 3 down. It'll cancel with the 3 in the 3 times 2 times 1. So you still have 2 times 1 in the denominator. And so the negative 8 divided by 2 is negative 4x to the second. And the next one, I would bring my 4 down. It's going to cancel with the 4, but I'm still going to have 3 times 2 times 1. And I'm going to have 16 in the top. And 3 times 2 times 1 is 6. So 16/6 is going to reduce to 8/3. So this is going to be 8x to the third divided by 3. And I'm looking at my paper because I simplified them. On my paper, I did not, but I think it's good to have them simplified. But if you didn't, then you might have had, you know, like just bringing the 2 down times the 4 is 8, but leaving that 4 factorial or 2 factorial there instead of changing it to 4. And then, well, that one was this one, bringing the 1 down. Wait a minute, what? Negative 2, oh, okay, yeah, because I'm taking the derivative of this, so this one right here. But on my paper, it was just everything just not simplified. So if you wanted to see it, what it would look like not simplified, where this one is the simplified version of it. Minus dot dot dot. And then if you wanted to do the summation for this one, n equals 0 to infinity, it's easier to look at the one that's not simplified to figure it out. I'm still going to have my n factorial on the bottom. I still need my negative 1 to the n. Only if I start with 0, I'm not going to get my first term to be negative 2. So this time I need to start with 1 because I want to make sure that whatever I start with, that I will be able to get this first term here, negative 2. And so at this point, if I put a 1 in, I'm going to get negative 1 divided by 1. And so then I just need 2 to the 1. Well, if it's 2 to the n, then that will give me, when n equals 1, that will be 2 to the 1. And then if n is 1, I think I want my n here and my x to the n minus 1 here. So let's see if this works, okay? So when n is 1, I end up with negative 2. When n is 2, that would give me a positive. 4 times 2 is 8, which I do have 8 in the denominator or in the numerator, and then 2 factorial in the denominator, x to the first power. So yes, I do get 8x over 2 factorial. And then when n is 3, I would get a negative. I would get 8 times 3 is 24 on the top, x to the second divided by 3 factorial. So you can see how, you can make it so that you get the same values. So that was our Maclaurin series, and we found the Maclaurin series for f prime using that f of x equals e to the negative 2x. All right, so let's move to the next page. We've got example number 2, evaluate the indefinite integral as a power series and find the radius of convergence. So what we want to think about is, we want to think about our integral. Well, first we need to recall that 1 over 1 minus x, if we, and these are in your calculus book, there's a few of these Taylor polynomials that are Maclaurin, actually, Maclaurin polynomials that they want you to just kind of memorize. And this one is one of them, 1 over 1 minus x. And so this is the summation from n equals 0 to infinity of x to the n. And so if I multiplied this by t, imagine that this was 1 over 1 minus, and then made my t cubed. So what are we doing? Well, we're basically putting t cubed in for the x. So this is going to be summation n equals 0 to infinity of t cubed to the n. So that's going to be t to the 3n. And then if I go and multiply by t, okay, so I'm going to take that off right now. But on my next step, I'm going to say, okay, now what if I multiplied by t? What is that going to give me? Summation n equals 0 to infinity t to the 3n plus 1. And so this is something that we are asking. There are a few of these Maclaurin polynomials that we want you to memorize, and this happens to be one of them. So when I see this integral of t over 1 minus t cubed dt, and I've already created that summation. So I've created that summation starting with 1 over 1 minus x. And I'm going to say that's the integral of the summation t to the 3n plus 1. And so, and since I'm integrating it, this would be dt. So I'm integrating a summation. So I'm going to say, well, I want to integrate, and I'm going to start with 0 and put all my values here. So if I get a 0, that first thing is a t. Plus, for 1, I'm going to get t to the 4th. Plus, for 2, I'm going to get t to the 7th. Plus, for 3, I'm going to get t to the 10th. Plus, and then for 4, I'm going to get t to the 13th. So there is your summation, your first 1, 2, 3, 4, 5 terms. And we're going to integrate each one. So you integrate term by term. So integration of t is 1/2 t squared. Integration of t to the 4th is 1/5 t to the 5th. Integration of t to the 7th is 1/8 t to the 8th. Integration of t to the 10th is 1/11 t to the 11th. And integration of t to the 13th is 1/14 t to the 14th. And then plus dot, dot, dot. And then plus, here is your term, t to the 3n plus 2 over 3n plus 2, and then plus c. So let's see. If your n is 1, that's going to be t to the 3 times 1 plus 2. So I think we're going to start with n equals 0. Summation n equals 0 to infinity. So if it were 0, it'd be t squared over 2. If it were 1, it's going to be t to the 5th over 5. If n were 2, it's going to be t to the 8th divided by 8. So you can see that by knowing where to start. You're either going to start at like 0, 1, or 2. I mean, occasionally you have to start at bigger values, but, oops, I was going to try or no, that was right, wasn't it? This was right. I was going to go like that so that you can see where, because this was my recall. But this would be like your nth term. And so now, since we know that our integral of t over 1 minus t cubed dt is equivalent to some constant plus the integral as n goes to 0, from 0 to infinity, of t to the 3n plus 2 divided by 3n plus 2. Then by the ratio test, we've got the limit as n goes to infinity, absolute value of t to the 3n plus 3 divided by 3n plus 3 times 3n plus 2 divided by t to the 3n plus 2. And that absolute value. I'm going to go ahead and add a page here. And so we'll go down here. I don't have a lot to do, but that is going to equal the limit as n goes to infinity. And we're going to look at our t to the 3n plus 3, t to the 3n plus 2. That's going to leave you with 1t. And then 3n plus 2 divided by 3n plus 3, that's actually going to end up going to 1 as n goes to infinity. Because you would really be focusing on the 3n over 3n, and that goes to 1. And so as n goes to infinity, this becomes t. And so we should probably put our absolute value signs on, Absolute value of t has to be less than 1 for it to converge. And so the radius of convergence, that's using the ratio test, less than